Okay, let's recap some of our class discussion about complex number basics. When I asked everybody what they remembered from Algebra 2, everybody remembered square root of negative 1, but that was about it. Why should we treat this as a number? Here's what some textbooks say. It's not a very good answer. So let's look at it. Let's decide it's not very good, and then let's move on. The real answer for why you should take this seriously as an actual number is a little bit more complicated, and we'll get there. But the reason that a lot of textbooks give is so that every quadratic equation, every degree 2 equation, will have two solutions. So on this side, we see that it does have two solutions because we can solve it by isolating the variable. So x is plus or minus square root 1, which is just plus or minus 1. You can see it works by plugging it in. Okay, well, what about this side? This side doesn't seem to have any solutions because if we isolate the squared term and then we take square roots, we get plus or minus root 1. But the square root of a negative feels like nonsense. And so before Algebra 2, before somebody told you that you should take this seriously, you would have just said, oh, this doesn't have any solutions. So a lot of textbooks said, well, look, we should want it to be true that every x squared equation should have two solutions. And so if we treat this as a valid number, now it does. That doesn't feel like a very satisfactory answer, especially when you think about the connection between solutions and roots. So if I think about the roots of x squared minus 1, x squared minus 1 is a downshifted parabola that looks like this. Plus or minus 1 show up here and here as the x-intercepts. Well, what does this one look like as a function? I've got an upshifted parabola that looks like this. So it makes sense that if you are finding a square root of a negative and you think that that doesn't mean anything, well, look, it doesn't correspond to any x-intercepts. So that's kind of consistent. And that's what people used to think. They used to think that when you have a square root of a negative, that just happens in situations where the thing you're trying to find doesn't exist. If, in this case, we're trying to find x-intercepts. So the thing that changed everybody's viewpoint had to do with solutions of cubic equations, and that's going to be a story for another time. But for the moment, let's just agree to postpone your skepticism, and let's decide that should be a number. We should be able to add and subtract them. We should be able to multiply them. We're just going to treat them like numbers. So let's give this number a name. We're going to name this I. Everybody in class wrote down square root of negative 1 equals I, which is not wrong, but I think it maybe misrepresents the situation. If you write that it equals I, it feels like maybe we're deciding that two separate things are really the same. We're discovering they're equal. That's not really what we're doing. We're just naming this quantity so that way we don't have to write square root negative 1 over and over again. We could name it Bob. So in that case, if you want to know what are the solutions to this equation, it would be plus or minus Bob, because Bob is our name for square root negative 1. So whenever you see anything with I, if somebody says the solutions are plus or minus I is not, some separate thing. I is just the thing we write instead of square root negative 1 because we're lazy. Okay, let's move on to the next question, which is, if this is a number, where does it live? In elementary school, I had a number line, like in my classroom, like when I was in elementary school, there was a number line way up close to the ceiling that looked like this. There were no negative numbers. I don't know why. And we were told that the number line is like the home for all numbers. Every number lives on the number line. And then later on, when we learned about negative numbers and we said, oh, hey, wait, there doesn't seem to be a home, they said, well, okay, look, we'll just extend the number line this direction. And so now there's a home for negative numbers also. And later on you learn about different types of numbers. So fractions like 1/2, 2/3, those live on the number line. They're just between the integers. Square root of 2, that definitely lives between the integers. Pi, that works too. So it seems like every single number lives somewhere on the number line. Let's ask, does square root of negative 1 fit in on the number line somewhere? Like maybe square root of negative 1 lives somewhere between negative 1 and 0. Or like maybe it lives between 0 and 1. Could it live somewhere on this home for all numbers. So let's think about it this way. Here are all the positive numbers. Here are all the negative numbers. And here's 0. So let's give square root of negative number the name m for mystery. And let's decide, could m live anywhere in here? Like, could m be in there? Could m be in here? So here's going to be the argument. Let's square both sides of this equation. So square root of negative 1 squared becomes negative 1. M squared becomes m times m. So we want to know, what could m be? So could m be positive? Decide right now in your mind, why or why not. Could m be negative? And could m be 0? See if you can come up with an argument for each one of these questions. So it seems like m can't be 0, because if it were 0, we'd have 0 times 0 equals negative 1, so that doesn't work. Could m be a positive number? Well, a positive number times a positive number is positive, so it can't be negative 1 either. Could m be a negative number? Well, a negative times a negative is also positive. So it seems like we have a good reason for feeling like m can't be any of those things. But this exhausts every possible location on the number line. So where does I live? So I, square root of negative 1, can't live anywhere on the number line. So just like in elementary school, when we decided to extend the number line in this direction so that negative numbers would have a home, we're going to extend your elementary school number line one more time. Only this time we're going to extend it up and down. So it's now a number plane instead of a number line. And the reason we're doing that is so that we'll have a new home for these new kinds of numbers. So the number plane, like I said, is an extension of the number line. We usually call it the complex plane. But like the way you want to think about it is it's just the home of all numbers. So just like the number 1 lives here and the number 2 lives here, the number I lives right there. It lives above 0. How this will make sense is something that will happen for you through time. But right now, like, that's the way to think about it. We've decided to extend the number line to a number plane. So let's talk about other kinds of numbers that might involve negative 1 as part of them. So there's 2 different ways of writing down complex numbers. And complex numbers are numbers that have a real part and some part that involves some multiple of square root of negative 1. And this is usually called the imaginary part. Don't be misled by the name imaginary. They are perfectly fine, normal numbers, just like any other numbers. They just happen to have the unfortunate name imaginary. So, again, using our convention, I'm going to rewrite this as 3 plus 2i, but remember that I is really just shorthand for times root negative 1. This is called the rectangular form because this tells you how far left and right the number lives, and this tells you how far up and down the number lives on the number plane. So if you had 0 i's and you just had the number 3, that tells you, oh, it lives, over by 3 on the number line. If you just had 0 plus I, that lives up by I in the complex plane. If you have both parts, a real part and an imaginary part, the real part tells you how far over you go. The imaginary part says how many square roots of negative 1 you have, and so it's sort of how far up do you go. So this is a single number, 3 plus 2i. Even though this looks like the xy plane where you represent a point with 2 separate numbers, we're representing a single number that just has 2 separate parts. Just as a side note, this is not the first time you've thought about single numbers that have 2 separate parts. Like if I have 2 plus root 3, that's a single number, but I have to write it down using 2 different pieces that I can't combine together very easily, unless I write out like an infinite decimal expansion. So we're going to come back to this analogy in a minute. For now, that's the rectangular form for a complex number. So you could say, like, that's z. There's a different form for writing them down, similar to when we had vectors, which is the polar form. I'm going to give you maybe a non-standard way of writing the polar form, and I'll tell you why in a minute. So for our polar form, we're going to write it this way. We're going to write the distance from the origin, so that's like the magnitude, and then we're going to write the angle. So for example, if I had this point right here, in rectangular form, that would be 1 plus I. In polar form, that exact same point, I would describe as that distance, its distance from the origin, and the angle. Well, the angle is very clearly 45 degrees, or pi over 4 radians. How are we going to think about that distance? Let's kind of zoom in on that triangle. So here's the triangle. I'm going to draw the complex plane. Here's I, here's 1. Okay, so what is that distance? We can use the Pythagorean theorem. So we can say, this is distance 1, this is distance 1, so square root of 1 squared plus 1 squared is root 2, and so this distance right here is root 2. So here's a common confusion that students often have. They say, well, wait up, how can this distance be 1? I thought that when you go up, that's I. So let me give you an analogy here. Let's just think about the regular old number line. So here's 1, here's 2, here's -1, here's -2. So if I put a dot here and I say, what's this coordinate? You would say, oh, the coordinate is -2. If I say, what's this distance? You'd say, oh, that distance is 2. And I might say, well, wait, how can this distance be 2 if that point is -2? And the answer is, it's 2 in the negative direction. So distances are always positive numbers. But here you see that a distance could be in the positive direction or in the negative direction. And if you travel the distance in the negative direction, you end up with a negative coordinate. So that's all that's happening here on the complex plane. If I put a point here and I say, what's the coordinate? You'd say, oh, that's I. If I say, what's this distance? The distance is 1. It's just a distance of 1 in the I direction. Just like if I go to the right, that's a distance of 1 in the positive direction. So again, on the complex plane, all distances are still positive. They can just happen in different directions. Okay, if you're into writing stuff down for notes, you could take a little note that says all distances are non-negative real numbers, even when they are in the imaginary direction. Okay, so where did we land here? The 1 plus I complex number could be represented in polar form as a distance of square root of 2 in the pi over 4 direction. So here I'm saying if we aim ourselves in the pi over 4 direction and we go that distance, we end at the same spot. So these are the same as each other, just two different ways of describing a single number. I think I'm not going to tell you more about the actual notation for polar form. Well, I will a little bit. So it involves raising e to an imaginary power. And I don't want to talk about it right now because I want this to make sense. And right now you don't have any way of making sense of what should it even mean to raise e to an imaginary power. So we'll come back at the end to sort of how this actually does make sense and why you should pay attention to it. But for right now, let's use this as our notation for polar form. Okay, we'll end the video by reviewing how do you add and multiply complex numbers together. So if I have a complex number, 1 plus I, which would be here on the complex plane, and another number, -2, -2i, which would be here on the complex plane, you add them with their separate components separately. So 1 plus I, -2, minus 2i. So the 1 and the -2, I can do 1 plus -2, so that's -1. Here I can do I minus 2i gives me -I. So you combine the real part separately and the imaginary part separately. So I end up with -1 minus I. This works the same way that vector addition works. So if I imagine following a vector, like a position vector that goes to the first complex number, and then from that point I add in the other vector, that takes me to the point that I actually ended up with as their sum, so the -1 minus I. So you can think about it just the same as vector addition. Okay, what about multiplication? So let's do a squared for a minute. So 1 plus I times 1 plus I. So in this case, it might make sense to distribute, like multiply out. So here, 1 times 1 is 1. 1 times I is I times 1 is also I. And then I times I is I squared. Okay, so the I and the I can come together as 2I. The really important thing is this I squared. So remember, I is just square root -1. If I square both sides of this equation, you get that I squared is the same thing as root -1 squared, which is just -1. So what that means is that whenever you see an I squared, you should immediately rewrite it as -1. So if I do that, now I've got 1 plus 2I minus 1, and that really just equals 2I. And so that's the final answer. So whenever you're multiplying complex numbers in the rectangular form, you would just multiply them by multiplying out the same way you would any binomial. But then you're going to end up with an I squared term, and just remember to substitute back in. Okay, so I told you the geometry of adding complex numbers works like vectors. What's the geometry of multiplying complex numbers? Here was my point A. When I multiplied A by itself, I ended up here, is where A squared is located. So there actually is a geometric transformation that's happening when you multiply complex numbers, and it's actually super important. It's kind of the key to a lot of interesting phenomena with complex numbers and complex functions. That's going to be for a separate video.